Hello everyone, welcome back to Exam Ignite. This is a continuation of the module 1, that is part 2 video of the microcontroller BEC405A for the VTU 4th semester 2022 scheme. So already in the part 1 I have discussed about the differences between microcontroller and microprocessor, RISC versus CISC, hardware and Princeton, and about the 8051 architecture. I'm continuing that architecture part here a little, that is special function registers I'm continuing here, and I'll be discussing about the ports and the external memory interfacing. So firstly, list out, it may be asked like this is a question that was asked, list out the different bit addressable SFRs, that is special function registers, available in the 8051. So the group of registers implemented to perform the special functions and located immediately above the 128 bytes RAM, it is SFR. It can be accessed by the names or by the address. So for example, register A, either it can be mentioned as register A or with the address E0H, or register B with F0H. So like that. So some of the functions that are given, A is for accumulator, E0, E0, then DPH, you can observe it as having address 83, DPL for 82, IE, IP, and P0 to P1, then PCON, SCON, all the addresses are mentioned here, go through them. Next is stack operation. Here, the area of the internal RAM that is used by the CPU to store and retrieve the data quickly is called as a stack. We are using stack pointers. Here it is used to access the address, and it is an 8-bit register. It holds the internal RAM address, called the top of the stack. When 8051 is reset, the stack pointer sets to 07H. So when data is to be placed on the stack pointer is incremented by 1. That is given by SP plus 1. The stack grows up as the data gets stored. When the data is retrieved, the SP decrements, that is by 1, that is given by SP minus 1. To store the data into stack, we use a push instruction, and to retrieve the data, we use a pop instruction. So RAM location here is 08H, let us consider, is the first location used by the stack to store the data. So move SP 40H and move SP 80. So here what happens here is, so SP after reset, it will be pointing to here. When SP becomes 1, it moves from the 7 to 8. 40 is moved from 7 to 8. So if SP plus 1, then we will move 30 to 9 through the push operation. When so finally it will be like this, 30 will be in 9 and 40 will be in 08. So when we use a pop operation, it becomes SP minus 1, and it points to, again from the 30 it points to 40. So this is how it happens. So default value of the stack is 07H. So program can modify based on that. We can change the stack pointers. So here you can observe CPU action. It is done. It's a stack pointer 7. It will move to 8. When we increment, it goes on incrementing like that. So address will also get incremented in the same way. And finally, we store the data, and finally we get the data through that stack pointers. So here it is a storing data on the stack. It is done here. That is incrementing through the incrementing and then storing the data. Here it is what it is stored in the internal RAM. Finally, we get the data from the stack, that is get then decrement. Next is internal RAM organization. It is one important question that was asked. So memory organization, here we are having two memories, RAM and ROM. RAM for data memory and ROM for program memory. As I said, we are having 4 register banks. Each register will be having from R0 to R7. You can observe here R0 to R7. So this is our working register. And next comes here, you can observe it is a byte address, and this inside one is a bit address. That is from 7F to 78. Like you have to go like this, from 00 to 07 it is present, from 08 to 0F, then from 10 to 17, 18 to 1F, 20 to 27, 28 to 2F. It goes on like that. So finally, we are having general purpose till the 7F. On explaining this, RAM is in 128 byte, that is of 3 parts. We are having working register, bit addressable register, and a general purpose register. What does this working register? Here, as I said, it is having 4 banks. 00H to 1FH, that is 32 bytes of RAM memory, contributes the 32 working registers. 4 register banks from 0 to 3, each having 8 registers. Hence, 4 8 it is 32. Each register can be addressed by the name or by its RAM address. Only one register bank can be used at one time. And please note this. And also bit, that is RS0 and RS1 in the PSW, determine which bank of the register is currently being used, as I said it in previously, based on the combination of that. Default register bank is always bank 0 is selected. Next comes second one, that is bit addressable register. It is of 16 bytes, occupies the RAM bytes address from the 20H to 2FH. That is 128 addressable bits. So that is what 16 byte into 8 bits, so 128 bits. 8-bit register, addressable register may vary from any byte address from 20H to 2FH. Example is bit address, that is 4FH is 7-bit address of 29H byte address. It is used in switching on and light of example for that where it is used. General purpose register is the area above the bit area from the 30H to 7FH, that is addressable as bytes. Next comes the ROM, that is programmable memory. We are having two types of ROM, one is internal ROM and external ROM. Internal ROM is of 4K bits bytes with the address 00H to 0FFH. So you can, it was mentioned there, using the PSEN and EA bar. That is external access, that determines whether the external memory is accessed or the internal memory is accessed. Then the external memory here, enable EA bar, it is connected to the VSS for the ground. Then the 8051, it has to get low, it has to set to the ground, this enable pin. Then you can say you can access the external memory from the other connected external. This enable should be 0. Next is oscillator circuit and timing diagram. All the internal operations that are synchronized by the clock pulses generated by the crystal oscillator. 8051 provides XTAL1 and XTAL2 pins for connecting a resonant network to form an oscillator. Quartz crystal and a capacitor is used. Minimum frequency of operation is 1 MHz and maximum is 16 MHz. So you can observe it is our 8051 microcontroller pin, XTL2 and XTL1. It is C1 and C2, 18 and 19 pins. So ceramic resonator or the crystal. Then one machine cycle, you can observe one machine cycle means it is having various states, and in that we measure the ports. So here 8051 timing, it is shown here. You can observe one machine cycle means it is having 6 states, and one state will be having 2 pulses. Here one state means the area between here to here. So it is having how many? 2 pulses. So smallest time needed to execute any simple instruction is called as a machine cycle. Time needed to execute is, there is a formula based on it. You may get a problem on this topic. So time needed, that is time instant, is C into 12, that is capacitor into 12 divided by crystal frequency. For example, let us solve a problem. Calculate the machine cycle at 16 MHz, 12 MHz. So they have given me F 16 MHz. So T calculation is 1 by F. You will get it the T. One machine cycle is how many? 12 pulses. So multiply that time with the 12. You will get the machine cycle. Similarly, for the 11.0592 MHz, find the time instant. That is what C is equal to 4 they have given. So 4 into 12 divided by crystal frequency. That is 11.0592 MHz. You'll get 4.34 microsecond. These are the two types you can expect. Schematic to interface external RAM and ROM. So here on this topic, you will be having the you have to design by placing the external ROM and external RAM and connecting it with the 8051. So accessing RAM, it can access up to 64 bytes of data from the external data memory. We use here MOVX is the instruction that is used to access that. So for example, you see internal RAM. Here it is, we are having lower 128 bits and upper 128. Addressing ranges 00H to 7FH. Here it is 80H to FFH. Registers, here you are having working register and general purpose register, SFR register. SFR, it can access by the indirect addressing only lower 128 bytes, either in the direct or the indirect addressing. So you can observe here, it is an accessing the external data memory. We are having 8051, we are having a latch, and we are having the external RAM. Here for the port 2, we are connecting it to here, and also you can observe the write and the read bars are connected to the write and the OE bar. And enable pin, it is connected to ground, so that it is said we can do some external connection for the memory. Then for the port 0, it is having with the digital pins, digital data lines. This is our timing waveform for the external data memory read cycle. Next comes external memory can be accessed by what? Read bar and write bar. Read bar is 0 means a data byte can be read from the RAM location. If write bar is 0, a data byte can be written into the RAM location. Now comes ROM, accessing ROM. So EA bar, that is VCC, that is if it is enabled as VCC, then 8051 fetches the address from the internal ROM. If the enable is 0, then only it will fetch from the external ROM or EEPROM. So if ALE is 1, then port 0 contains the address bus, that is A0 to A7. If ALE is 0, then it will connect the data bus, that is D0 to D7. 74LS373, it is used to demarks the address and the data bus. So it is enabled when the ALE is 1. So therefore the output of the IC has a lower order address, that is A0 to A7, has PSEN, that is active low signal, connected to the OE band to access the program code from the external ROM. Here you can observe this is our 8051, we are having a latch and we are having a ROM. So from the port PSEN is connected to OE bar, then from port 2 we will connect the address lines, and from port 0 we connect to the data lines. So this is our timing diagram. Next comes I/O ports, an important topic. I/O pins or the ports and circuits. One major feature of the microcontroller is versatility built into input-output circuits that connect to outside. So DIP, dual input pin, has 40 pins. So 24 pins each of use for one of the two entirely different, yielding a total pin configuration of 64. So function of this depends on what it is physically connected and the switch commands that is used in the program pin. We are having 4 ports, port 0, port 1, port 2, port 3. Each port that is output latch from the each pin. SRF, that is special function register. For each port, it is made up of 8 latches and the address bit at SFR address for that port. 2 data path to read the latch data and the pin data. 2 buffers are used, that is when upper buffer is enabled when the latch data are read, lower buffer is enabled when the pin data are read. Port 1, here it cannot be programmed, only port 0, 2, 3 can be programmed. We are studying it in detail. So starting with the port 0, it thus serves as both input and output, or we can be used together as a bidirectional low order address and data bus for the external memory. Let us consider it is used only for input for the case 1. In the case 1. So 1 must be written corresponding to port 0 latch by the program. Transistors are off here and the pin in the floating condition in a high impedance, that is state, and the pin is connected to input buffer. You can also, this is a pin diagram of the port 0 configuration. In this the transistor is off. If it is a input, acts as an input. Let us consider case 2. Here it acts as an output. So 0 must be returned to port 0, that is latched by the program. Here it turns on the lower FET and all the latches that are programmed to 1 still float. So thus the external pull-up resistor are needed to supply a logic high. We need an external pull-up resistors when using this port 0 as output. Case 3, that is port 0 is used as address bus to the external memory. An internal control signal switch the address lines to gates of the FET. You can observe here. Then logic 1 on the address bit will turn on the upper FET. Lower FET will get turned off. Lower FET will get turned off by providing a logic high at the pin. Similarly, when the address bit is 0, lower FET will be on and upper FET will be off. Finally, the address has been formed and latched into the external circuit by the AL. Now the bus turned to become a data bus. Port 0 reads data from the external memory and configured as an input. Similarly, we'll go to the port 1 where it does no dual function. So output latch is connected directly to the gate of the lower FET. So here it does not, here it was performing as two input and output for on and off, but here we are directly connected. You can observe here we are having 1 and it is directly connected, used as an input. So 1 is returned to the latch, here 1 is returned to the latch here. Then lower FET will get turned off from this latch. Then pin and input to the pin buffer are pulled high by the FET. So when it is used as output, latch containing a 1 can drive the input to the external circuit high through pull-up. Latch containing 0 will lower the FET on, and pull off pin can drive the input of external circuit low. Port 2, this can be used as input output both. It is similar to the port 1, can observe it is similar to the port 1, but except you can see this is not directly, we are having a control logic here. Here the control logic is not there. Alternate use of the port 2 is to supply a high order address bit in conjunction with the port 0, low order byte to address the external memory. Port 2 pins actually changes from the address control signals when supplying the higher byte of 16-bit address. So here latches are stable when the external memory is addressed. So control lines and address lines are given. We use a read latch and the read pin. Internal bus and write to a latch is provided. Then from the control logic, it determines and works. We provide an VCC input and internal FET pull-up. So hence it is a pin 2, port 2. Port 3, that is port 3 is an input output port which is similar to port 1. Again, here input output functions can be programmed under control of the P3 latches or control of various other SFRs. Each pin of P3 may have individual program. So that is used as input output or as an alternative function. Like if it is P3.0, then RxT, that is serial data input. For TXT, for transmitting, it is serial data output. Then into 1 means external input 0. Into 1 is external input 1. So this is our pin configuration of the pin 3. Here we are using a NAND gate which has a difference here. Same other things remain the same. The last part, the important part, is the external memory interface. So first question, we are having a 4K bytes of RAM and 8K bytes of RAM. We have to interface it to 8051 microcontroller in such a way that the starting address of the RAM is given as 1000H and the ROM is given as C00H. Let us find out the address lines first. So 2n is the memory size. So 2n is what they have given me here, 4K. So it becomes 4K bytes. So what 4K can be written as 2 power 2 into 1024 bytes. K can be written as. So 10 power 10 to 1024 can be written as 2 power 10. So it becomes 2 power 12. So the n is 12 address lines. This is for RAM. Similarly for the ROM, 2 power and memory size 8K, that can be written as 2 cube into 1024. That is 2 power 13. N is 13 address lines for the ROM. Starting address and ending address. So starting address, it was given as 1000. So 1, you have to write it in the 16 bit, like this is for 1 and this is for 0, and here again 0 and again 0. So only here you can observe it comes as 1. When you change it, this remains the same, and change all the zeros to 1. So it becomes a 12 address line, that is logic 1. So on changing this, we get 1 as 1 and this is FFF. So 1FFF is our ending address. So for the ROM, if you come, they have given me C00H. So here C means it is 8 plus 4, that is 12, and 0 0 0. Again it remains the same, and change this to logic 1, and they have said we need 13 address lines. So from here mark the 13, it comes till here. So this is my 13 address bits, that is logic 1, and changing this is my FFF, and here it is 13. So it is the FFH is my ending address of the ROM. On seeing the interfacing part, you have to first write the 8051 microcontroller, then ROM and RAM. ROM is of 8 bytes and RAM is of, as it is mentioned here, it is 4K bytes. Now here, first thing you have to make the enable has grounded so that it can interface from the external memory. Now firstly consider the port 0. In the port 0, the address lines are connected to a latch. Here the OE bar is grounded, and to this latch here all the address lines are connected from port 0 to port 7. Similarly, the data lines. Data lines here, that A0 to A7, it is connected to ROM. But actually, how many address lines do we need for ROM? The ROM, we need, as it is mentioned here, for the ROM, we need 13 address lines. So we got 8 address lines from this. So remaining thing, take it from the port 2. From the port 2, from 8 is done. So 9, 10, 11, 12, 13. That is 8 to 12. That is already here it is from 0 to 7. From 8 to 12 we will take, and it is connected to ROM. So next thing, remaining ports connected to a an AND gate and connected to CS bar. And also you have to connect the VCC here, and OE bar, it is connected to my RD bar, that is read bar. And next comes the RAM. RAM, as I said, it is having 12 address lines. So again this continues actually here. This continues, that is A0 to A7 will get continued here, and here only A8 to A11, not A12, only A11. So then remaining here you have to, again as it is a ROM, it has to get read bar and write bar. So connect it to the write bar and read bar from the microcontroller. And here also you can see the data lines of D0 to D7, it is connected to the ROMs D0 to D7, and it is connected to the RAMs D0 to D7. So to understand clearly, let's go with another one where 8051 microcontroller, which is having 8K bytes of ROM and 8K bytes of RAM, both are equal. So we are getting 8 into 1024, which is 2 cube into 2 power 10. So that is 10 plus 3 is 13. So samely here n is my 13. Write down the 8051 microcontroller, ROM of 8K bits and RAM of 8K bits. Firstly, start with the P0 to P7. Here we are getting 8 address lines that is connected to the latch, and that we have to connect it to the ROM, and then again that will be connected to the RAM. So here 8 lines are done. So remaining, how much do we need for the 13? Remaining things, take it from this 8 over 9, 10, 11, 12, 13. That is 8 to 8, 12. That is connected to RAM, and that continues to the ROM. So remaining pins is connected to CS bar. Also you have to note, enable pin should be grounded, read and write signals to be connected to the RAM, and OE bar for the read signal, and connect the VCC for the both the RAM and ROM. So finally, don't forget to connect the data lines, all the D0 to D7 for the microcontroller to the RAM and to the ROM. So this completes the complete module 1 of the microcontroller subject. I hope this is clear for you. If you have not understood, go back and go through my handwritten notes. It is easily written and it is very easy to understand. So thank you for watching. Do share, like, share and subscribe to my channel. See you in the next video. Stay updated.